My name is Udi Vijayawardena. I'm the Alumni Engagement Manager for the Faculty of Science. It's a great pleasure to welcome all of our alumni, local and also international today. Um, Before we start the session, I'd like to acknowledge the traditional owners of our land and pay respects to our elders, past, present, and emerging. If there's any members in the audience who are from Aboriginal or any other Indigenous backgrounds, I welcome you to country as well. In terms of our alumni community, we've got about 43,000 alumni and about 110 different from about 110 different countries. So it's a big community, and they come from all different walks and paths in science. Today's session is presented by the School of Earth, Atmosphere and Environment. Associate Professor Ruth Reef is the presenter today. Without taking further time, I'd like to introduce the moderator for this afternoon, Dr. Sabrina Sayers, who's just in the screen there. There's Sabrina. Now, Sabrina is a PhD student, a post-PhD student, I would say, of Ruth's, just finished a PhD. She has been working in the space of the drones and currently focused on drones to capture images of vegetation structure and temperate mangroves in Victoria, and doing these images and using them for biogeomorphological studies. Now, Sabrina probably has to explain it a little bit further for all of you who are joining in. She currently works as a remote pilot and a technical research officer within the Monash Drone Discovery Platform. So Sabrina, I'll leave the session with you if you'd like to introduce the session and a little bit of housekeeping for the questions as well.
Thank you, Udi, and thanks for having me moderate, and thanks for the introduction. So tonight we have Associate Professor Ruth Reef, my former supervisor. I think she's happy that I'm finally done. And before we start, I'm just going to give a brief introduction to Ruth and her work, and then we'll get into the session for this evening. The presentation should take about 30 to 40 minutes, and then we'll have some questions, which I'll write down and pass on to Ruth as the session goes. So to introduce, Ruth is an academic at the School of Earth, Atmosphere and Environment, and she's also the Dean of undergraduate education in the Faculty of Science. Following several years in the military and a short stint as a park ranger, Ruth started her academic career with a Bachelor of Science at the Hebrew University of Jerusalem, Israel. And that ignited a passion for marine science and laid the foundation for her future endeavors. Building on her undergraduate studies, she pursued a master's in physical oceanography from the Inter-University Institute for Marine Science in Eilat, followed by a PhD in marine science from the University of Queensland, Australia. This solidified her expertise in coastal dynamics and really propelled her to the forefront of the field. From 2012 to 2015, Ruth was an Australian Research Council DECRA Research Fellow at the University of Queensland. And between 2015 and 2017, she had the privilege of being a Marie Curie Research Fellow at the Cambridge Coastal Research Unit at the University of Cambridge in the UK. And this broadened her international research collaborations, and we still benefit from those today. Since 2017, Associate Professor Reef has been an integral part of Monash University's academic community. Throughout her academic journey, her research has focused on understanding the dynamic interactions between shorelines and environmental forces, encompassing natural disturbances, human impacts, and climate change. Her work combines numerical modeling, experimental techniques, and advanced remote sensing methods, such as UAVs, to unravel the complexities that govern coastal systems that lead to shoreline change and measure greenhouse gases and water exchange between coastal ecosystems and the atmosphere. This sheds light on their role in climate regulation and coastal subsidence. Additionally, she has explored the biogeographic response of coastal species such as mangroves and seahorses to global change. She's also incorporated species distribution modeling to guide conservation efforts. Associate Professor Reef has a steadfast commitment to scientific excellence as she continues to explore the fascinating world of coastal research as the head of Monash's Coastal Research Group, and she has contributed significantly to the sustainable management and preservation of invaluable coastal habitats. And I was actually very thrilled that she picked me as one of her PhD students, and I got to learn from her for 4 years. You guys only get her for 40 minutes, so we'll just start now. Thank you.
Thank you very much, Sabrina. As always, excellent. So if you want to know more about the work Sabrina has done, she's actually published it, and it's available open access, and you can look at things Sabrina has done and others from our group. Today we're going to talk about coastlines, and these days when we talk about coastlines, we keep talking about coastal erosion. We're worried about sea levels, but what I'm going to show you today is what these dynamic systems usually look like, and what we might expect in the future, because it is a bit of a hot topic, and there are some things we understand very well, and there are things we still need to explore. Now, what I have in the photo here, this is the mouth of the Daintree River. There's eagle-eyed amongst you might spot a crocodile down there. But a lot of the talk is going to focus on what we call low-energy shorelines, because when we imagine shoreline and shoreline change, we often imagine those big beaches with big houses falling and swimming pools falling in. But actually, that's not where we live. We live on the estuaries, on the embayments around our coast. And so we're going to focus a little bit more on these habitats rather than open coast. So Australia is a coastal nation. I'm sure many of you are aware. We go to the beach a lot. It has the 6th longest coastline in the world. So those of you out there in management are very aware of the size of things we need to manage. Hold on, I'm just going to move all this Zoom stuff. So we are very coastal in our culture, and we have been, especially Indigenous Australians have been the sea country has been integral in the culture and still is, and has been for many millennia. So Indigenous Australians, but also people from many other countries around the world view the coast as it's perhaps our most preferred habitat as a human species, is that very narrow strip of land between the sea and the continent, right? We really like that place as species. And for Australia, it's especially prominent. 90% of Australians live within 50 kilometers of the coast. And if I look in news headlines, right, for example, using Factiva or one of those databases, and we just look at the term coastal erosion, when did it make headlines? And we can see not only that it's become far more in the front of our minds, it kind of comes in waves. And these waves are something we're going to talk about, because we have periods of certain climatic periods where those things bother us more than others. But it's really important to realize that as we can see from Indigenous Australians, of course, they've been here for a very long time, and they understand the system very well, and they've seen coastal change. And they describe coastal change. And wherever we lived we've seen this as a species. So we have a few plots now that are a little bit different to read. I know everyone's a scientist, but I'll just explain what these plots are. And we're going to look at what sea levels have been doing to this day. And we have a pretty good idea for the last 600,000 years. And we get this good idea from all sorts of paleo markers that I won't go into the detail of, but there are things to do with sediment cores and oxygen isotopes, or for example, we can see things through coral reefs. And so there are all sorts of these paleomarkers that enable us to see what sea levels used to be. And what we have here is on the x-axis, going from right 450,000 years ago, going left to the present, which is 0. This is present day. And then we can see the sea level as it is relative to today, which is this dotted line. So RSL is relative sea level. And we can see that sea levels went up and down, and they go up and down. So we live on planet Earth, and we have a certain amount of water, and we don't share water with space. So what we have is what we have. So if it's frozen in periods of glaciation, it's not in the ocean, right? So we have oceans drop when things get very cold. So our species, Homo sapiens, has been around for quite a while. It's been recognizable to us for about this period of time, so 120, 130,000 years. And during our time here on the planet, we've seen sea levels be a little bit higher than today. We've seen sea levels much lower than today. And when we look at what we really recognize as self, in kind of the societies we occupy to this day, we're looking at the Upper Paleolithic or similar types of eras in all sorts of cultures. We can see that actually we've formed our societies during periods where sea levels were about 140 meters lower than they are today. So our society, that's quite well documented through oral histories and even through writing, has seen sea levels increase 140 meters. But the last 2,000 years has been relatively stable. So what does a world with sea levels that are like 140 meters lower than today look like? It means that a lot, so we have continents pretty much floating, right? And we have areas of the crust that are lower, and they're full of water, so they're the oceans. But sometimes more or less of the continent is exposed, depending on how much water there is. So I have my little cake, and I can fill it up with custard, and there's more or less cake exposed, right? So when we lower the sea levels, we see things like Australia and Papua New Guinea are one piece of land. There's some lakes in there, but there's mainly you can just walk here. It's a long walk. Tasmania and Australia are connected. They're big shelves that are exposed. The Great Barrier Reef is mostly just exposed land. What was the Great Barrier Reef? And we see that same. I mean, like the United Kingdom is connected to Europe. Of course, there's a big ice sheet, so it's not like you can walk there, but there's a lot of the ocean's continents are exposed. And then comes a period of melt, and it's relatively rapid. And during this Pleistocene period, we have, so this time our plot goes from 140,000 years ago on the left to the right, and we don't have a good convention of is it right to left, left to right. It depends on if you're an archaeologist, if you're a paleoclimatologist, and we can see the rise in blue of sea levels. And we can see here's the Holocene, and we are here pretty much in this curve that didn't change much, but people were here and they saw this. They saw it happening before their very eyes, and we, to this day, have these stories. And that's wonderful. We have documented stories. We know of about 20 Indigenous Australian stories describing these events from 13,000 years ago. So the same way that there were periods of marine transgression, as in like the ocean came onto the land, like this melting, we also had periods where the ocean retreated. We had periods of time where oceans were higher than today. And those are important points to look at because, hey, what is the future going to look like? We have a little bit of a template. We can see things like, I don't know if you've been to Robins Island in Tasmania. Not a lot of people have, but it's here on the northwest corner of Tasmania. And there's like an area called the Remarkable Banks, because what you see are old shorelines, and you can date the shorelines. You can date, actually you can date sand, which is wonderful. You know when the sand was buried. And these old dunes, when the beach was all the way back here, was 130,000 years ago, and you can see where the ocean used to be and how it dropped over time as sea levels dropped. So oceans come and go, right? And currently we're in a period of, so we had an ice age, there was a lot of ice, now we're melting it, and we are in a period of sea level rise. So what does that actually look like on the coastline? And I've made this really rudimentary drawing just to get 2 points across. So we have a coastal landscape, okay? So here I have mangroves and a salt marsh, and I raise the sea level. And one thing I can imagine is I'm raising the sea level and the coastline is retreating. We call that coastal retreat. Sometimes when I have coastal retreat like that, I've already built a hospital or roads or cities, and I have a barrier to migration, and we call that coastal squeeze. So those are the things you'll hear. But the third thing I want to focus on today is actually when sea level rise, it doesn't mean everything has to translocate. We can raise the land alongside. And we're going to talk about that outcome especially. And when we think about shorelines moving, we always think about, well, my house is here and now the ocean is here, and that's a big problem. But what is even an equivalent problem from much of this is that the way we define boundaries in geography is linked to place and not linked to habitat necessarily, right? So we have about 40% of our intertidal zone is protected in Australia, but it's protected by boundaries where existing intertidal zones are, not where they're going to end up if they migrate. So we need to think about what happens when that whole system is moving. And I'll start off by saying we're going to focus on sandy shores, because the processes that happen when the coast is rocky, a rocky cliff, for example, versus when you have a sandy shore are a little bit different. Actually, most of the world has rocky shores. Here in Australia, we're less familiar with them because they're not here. We have a situation where our continent is very stable. So sea levels, when they rise, there's plenty of time for sand to settle on our basement rocks. So we have beaches. In areas where the rocks are rising quickly, you don't have time for sand to settle. So you have like these big rocky things. They also get impacted by sea level rise. You can imagine waves hitting this cliff a million times a day, or not a day, but a million times in a week, and vibrating it. So that erodes as well. But we're going to talk about sandy shores because they cover 30% of the ice-free shorelines of the world, and they cover almost entirely the Australian coastline. And they are retreating, right? This is kind of making sense. Sea levels are rising, shorelines will retreat. So we have a quarter of the world's sandy beaches are eroding at a rate of more than 0.5 meters a year. It's quite easy to see shorelines from space. Lots of different satellite-based programs exist to map shorelines, and these are just 3 examples. Many different papers show where shorelines are going to end up. And we can see that in some areas, shorelines accumulate, in some areas they retreat, but a quarter of them are retreating quite quickly. So why are sandy beaches so vulnerable? When the beach retreats, where's the sand going? And where did the sand come from in the first place? So those are 3 things we have to address first. So beaches are not standalone entities. they are part of a system of beaches called a compartment. Now, in Australia, I hear it called compartment a lot. Used to the term coastal cell, you might hear both. So we have what's called a dynamic sand budget. When you go to the beach today and you go to the beach tomorrow, the beach looks the same, but the grains are not the same grains. The grains you saw there yesterday have moved on. Okay, so we have like a snake of sand going from one beach to the next. And these beaches that are connected are part of the same cell. And the sand coming to that cell, it could be all sorts of sources. Mainly it's erosion, weathering products of rocks that are coming down the rivers. But it could also be local sources. So if you go to Heron Island, those of you who have done the Heron Island field trip, that entire beach is built of the reef that is surrounding it. So there are different sources for sand. Mostly we're talking about minerogenic sands that are coming down rivers. So that's where the cell starts. And then the sand travels through beaches, and eventually either it hits some sink where all the sand deposits, or it hits like a canyon or something that takes the sand down to the deep ocean, never to be seen again. And that's the end of that cell. But so what that means is if I manipulate a river, like I put a dam on it, or if I've placed a groin or some barrier or a jetty or something to the flow of sand over here, it means I'm going to starve beaches further down. So there are a lot of the erosion we're seeing and things like that, sometimes just to do with the fact that we messed with the sand budget. And these types of cell exist also in the low energy shoreline. So this is an example we did from Western Port, where we're looking at different sand types based on the geochemistry. So I can look at a grain of sand and look at what mineralogical composition it has and create these different groupings, right? And I see sand coming in from the Bass Strait, and that's like a type of end member. And we see that the beaches at the entrance to Western Port Bay, the bay right to our east, these Bass Strait sands, but they don't go into the bay. In the bay, we have other sources. We have 5 other rivers that bring sand, and we can see which beaches share and which don't. So if I make changes to the beach over here, I'm actually not influencing beaches further down, right? So we have all sorts of movement of sand that is to do with just sand is moving in cells. Sand also moves from the beach to the deep water and back, okay? And the time scale of that can be really quick. So this is a freak high tide in Ireland, took the beach away, and the next day it was back. So this sand isn't disappearing, it's just sitting in the deeper water. And when conditions are right, it comes back. There's a mystery pop-up beach in Tamarama. I mean, those of you who are in Sydney can check it out. Every 7 years, there's a beach there, and then it disappears. So to understand whether a beach has eroded, say because of sea level rise, you really need to spend some time looking at it, because there are processes that move sand laterally and from the shallow to the deep that are happening at all sorts of time scales. And in Australia, we're lucky to have a few places where these long-term records are held. So that's what happens at the beach. Low energy shorelines, shorelines where we don't have that much wave action. So we have significant wave height. It's a way to measure waves of less than 0.25 meters, which means you won't go surfing there. And if you have waves, they're just little wind-blown waves. They can still do work at the beach, but they don't have that much energy to move sand from the shallow to the deep. And all of that process we looked at is happening at much smaller scales. And they're far less studied than those open coast beaches, even though if we look at the distribution of low energy shorelines, are just cut off based on wave heights, where those occur, we can see that actually they're occurring where we live. it's not easy to have a port or have your whole infrastructure sitting on a very active, high energy beach. It's easier to be tucked away on a river estuary, and you also have more fresh water. There's a reason we gravitate towards these low energy shorelines. I want to shout out Robbie Bishop-Taylor, who you guys should look him up. He works for Geoscience Australia. He created this amazing product that is really driving kind of a way of thinking now about shoreline change. And basically, he took satellite records and over many, many years, he mapped where the waterline sits and like how that's moving over time. And we have millions of points now across Australia where we can see whether that waterline moved closer to land or further out, right? So in red and blue. And we have the rate of change over these since 1988. That's like since we have a good satellite record. So I took what Robbie and his team at Geoscience Australia created, and I picked out only low energy shoreline points, right? So there's about 1.8 million points. So these are really big data sets. And instead of, there's a little bit of a discussion in the literature whether the waterline is quite exactly the coast. Instead of going into that detail, right, I was just like, okay, is it translocating landward or is it not, right? So presence and absence of erosion. Okay, so so instead of saying how much things move, just whether they moved and whether they moved landward. So we take that big data set of points, and now we couple it with all we know about this system. So we know rainfall everywhere. We know the wind speed everywhere. We know the wave height everywhere. We know the suspended sediments, how much sediment, how much sand is floating around in the water everywhere. We know how the wind and the land angle interact. We know whether there's mangroves there. We know whether there's sea level. We know that sea level rise is not the same everywhere. I'll show you in a moment. But is so we can have all these different geographies, right? And combine them with what we know the shoreline has done. And of course, this is a huge task for our brain, but it's not a huge task for a high performance computer. So we ask kind of a machine learning model or a neural network, or we can use all sorts of computational algorithms to say, hey, find some links here, right? So, and what we get is a model. And this model is predicting the probability of erosion for any point in this system. And if I look at what Robbie and his team found here, and I look at what the probability of erosion the model is saying, they're not far off. I mean, like, obviously it's not a perfect depiction of reality, but it's a pretty good one. And not only is it a good depiction, at this point, I no longer need to know whether the point, what it's actually doing. I don't need the satellites anymore. I just need these layers to tell me whether erosion or progradation is happening. So if I look at my model and I ask my model, so what matters, right? What matters to make a shoreline change? We can see that erosion at these low energy shorelines in Australia is currently driven by sediment deficit, and it's not really sea level rise yet. So things like wind. So if I have really prolonged calm conditions, I have nothing suspending sediments. I have nothing to bring sediments to the beach. So I'm slowly eroding. If I have aridity, remember we need a river to bring sediments down. If you don't have rainfall, you don't have the sediment. So aridity drives erosion. And when we have higher availability of suspended sediment in the ocean, we have less erosion probability. Other things are contributing as well. And one of them, I just want to make a mention of sea level rise, because I don't want you to take home a message that sea level rise doesn't matter. It does. and it does very much. The only thing is that currently our sea level rise rates are not very high, but where we do have, so what you can see here is sea level rise rates around Australia over that period. And one thing you'd notice immediately is that they're not the same everywhere. And that's a really important point, right? Because sea level rise is not going to increase at the same rate everywhere around the world. And it hasn't so far. And we can see that there are some areas where sea level rise is a bit higher. And where you increase sea level rise, so if I keep everything else on an average level and just play with sea level rise, if I increase sea level rise, I also increase the probability of erosion. So another thing that pops up is that mangrove forests correspond to low erosion probability. And we're going to focus on that now. But I just wanted to mention that the next step, of course, is projecting. So I have a model. It knows where is there probability for erosion given the conditions. Why not project to the future, right? So we know what rainfall is going to do to a certain degree. We know what the wind is going to do. We know we have all these climate models that we can be using. What we don't have is understanding what sea level is going to do to this level of detail. And people like Professor Andrew McIntosh and Dr. Felicity McCormack from the School of Earth, Atmosphere and Environment are providing that important gap as we speak. So sea levels are rising. There are areas that have higher erosion probability than others. And we saw those are quick. People noticed the west coast, for example, of Australia. What do we do? Okay, so we have 3 options. We either we retreat. Okay, so we say, okay, we're going to move. We're going to not build here. We're going to, so that's called retreating. We can accommodate, which means now we are still here in this zone that's flooding more, but we're going to build higher. We've been seeing this a lot in the public discourse, to build on stilts, all sorts of things like that. An option, and I come back to the fact that we've been dealing with the sea level rise problem for our entire Upper Paleolithic, right? And that has been almost overwhelmingly protect, right? So if you're not saying, let's build a seawall, you are fighting 7,000, 10,000 years of building seawalls, right? So we have protect, we build a seawall, you hear that all the time. We have all sorts of soft defenses here in Melbourne. We nourish beaches all the time. We keep adding sand to our beaches artificially. And the third one is living shorelines, right? And I'll show you what that means. So living shorelines, living things on the shoreline. We have, based on the tide level, we have things that are below the tide, which is the seagrasses. We have things between the tides, which is mangroves. We have things at the upper tidal limit, salt marshes. These are all part of that living shoreline. And they are really instrumental in this, that there's a reason why mangroves matter when we look at projections of coastal change. And I'm going to just show this little video because it shows something I put in a flume a few years ago. So I have salt marsh plants here. Like just this grass called Puccinelia. Planted in a flume, and water is going to flow from right to left. And when you see the water flow through this grass, what you're going to see is that you get a slope. And this hydrological slope is because there's a retardation of the flow through the grass, right? And when I stop the flow, what's happening is anything entrained in the flow is going to start dropping out. So if we look in the field, and what you can see here is a very cold and miserable salt marsh in the UK near the Thames estuary called Tillingham. And in Tillingham, on this little part of the mud flat where the salt marsh just starts, I built a flume. And in the flume, I measured what sediments are coming through. So these are sediment profilers. They can tell me the suspended sediment load at any height above the bottom. And I have a current meter in here. And during the tides, the water comes in and comes out. And I'm just measuring what's coming in, what's coming out. And we look at what's coming in the flood tide, and there's some sediment coming in. That's the sediment budget. And I look at how much is coming out with the tide, and I look at, wait, so how much is left behind? And we can see that in this case, I cut vegetation, I did all sorts of manipulation, but what ends up happening is that there's always a net positive balance. Sediment always stays in the marsh. We are building land. And how much is staying depends on how much is coming in. We didn't saturate, like the more comes in, the more stays. Let's look at a whole river system now. So this is Will Stevenson Vissers. He was a wonderful honor student in our group, and he now works for WaterTech. And he was looking at what's coming in and out of an entire mangrove system by measuring what's happening in the creek. So here we have, again, sediment profilers, current meters, or water samplers. So we're taking samples this whole time. And what he found is whatever's coming in with the tide, 84% of that is staying in the mangrove forest. So if we actually measured how much sediment that is over an entire mangrove, over the entire mangrove, and covered it in that thin veneer, we'd have we'd have more than 4 millimeters every year. And those of you who are not familiar with sea level rise rates, we're like looking at less than 3 at the moment. So 4 millimeters per year, we're keeping pace with sea level rise. So let's look at it at more, globally. And we have this way of measuring how much sediment is coming in. We can see how much sediment is accreted at the surface. And actually, interestingly enough, I mean, like these numbers add up to similar to what Will found in his honors. And we have like 4 millimeters up to 7 millimeters a year, depending where you are. And we can put like a layer of something, different colored on the ground, feldspar, and see what settles on top after a while. But of course, the whole land moves. So you need to look at not just what's accreting at the surface, but maybe the compaction of the entire surface so that we know how it relates to sea level. So we have these sets of sediment elevation tables. The rod that goes in very deep, and we measure the distance from this rod basically to the land surface. And so when you accrete when you're accreting these pins, the distance is smaller, right? And if you are eroding and losing sediments, this distance becomes greater. But another thing it measures is if you combine this and that measurement, you know what's happening with deep subsidence. And we look at areas all around the Indo-Pacific. And we found that about 70% didn't have enough, couldn't keep up with sea level rise. And what mattered was how much suspended sediment is available, where there was enough suspended sediment. So what you see here is a map of just suspended sediment from a satellite, and you can see in darker colors where big, like the sediment is not equal around the globe. It's especially at river mouths, you can see outside of the Amazon. But where we have sediments near the shore, we have enough accretion to keep pace. And we can look through, so here in purple, you're seeing mangrove forests drowning. And in kind of what I thought was a green color, but is it, are mangrove forests still alive? And we can see that in some areas, up to 2100, these things are keeping pace. So but 2100, we're seeing no flooding happening behind these mangroves, right? So this is, these are really important shoreline defense systems. So the sediment doesn't only come from the ocean, it also comes from the land, right? And these wetlands are capturing that. It has other actual benefits. In this Great Barrier Reef catchment, we caught a lot of sediment that comes from all sorts of sources, but it's important to remember sediment supply to these marshes is not only coming from the ocean. So I'm going to start wrapping up, but what I'm going to show you here is that if we give these mangroves or salt marshes or seagrasses a place to be, they'll actually extend. And when we think about sea level rise and that movement inwards, what we're seeing is that they're going to take up more space. And when we look in Australia, we're seeing a big increase in the area of these intertidal wetlands. And these intertidal wetlands increasing in area, yeah, it's great for the area of the intertidal wetland, but it does mean that the shoreline has retreated. So we have areas in Australia where when we combine what the wetlands are doing and what the sediments are doing, where we're going to see that type of retreat, and more than other areas like down here in Victoria, things are quite stable. And I will jump to here because I'll end on this, which is, so we're talking about a system that is biologically controlled that could serve as a soft defense for sea level rise because of its ability to capture sediments and build land. But of course, biology is fickle. And we also have climate change happening. And I'd like to plug here the work of Dr. Maria Carmen Martinez-Diaz, who now works for CSI Roe in Townsville. And she looked at the biogeography of of mangroves and how they would change when climates change. So we're counting on them to, capture sediments here and there. Are they going to even be there, right? And there are certain areas where we'll see huge expansion of mangroves. So in the northwest, but down here, much less so. We're going to see a decrease for all sorts of reasons, mainly to do with precipitation. But important to note that when you work with living shorelines, they are living things, and we need to keep in mind that they might not be exactly where we want them to be. And when we restore, for example, ecosystems to take on this role of coastal protection, we need to think about which species it is we're going to use. Thank you very much. And I'll hand over to Sabrina to see if we have any questions.
Thanks, Ruth. That was very interesting. I know you could have gone on for forever.
Oh, yeah.
We have so far only one question from our audience. This is from Ashley Pang. And her question was regarding Robbie's model. I'm wondering, are all the factors like rainfall, wind, mangrove presence, and wave period, do they share the same importance, or is there one factor or a few factors that pay more significance, that are more significant than others in contributing to what's happening?
Thank you, Ashley. I'll just clarify that the shoreline change data is from Robbie's team in Geoscience Australia, but the model is not. And in this model, where we look, no, not all things are important. Some things have relative importance that is greater. In our case, it's wind. In this model, wind is a really strong parameter, and as is rainfall. So things that contribute to the creation of suspended sediment. And we don't find that wave period, for example, is playing a big role, or wave height, but it's important to note that these are low energy shorelines where the waves are not, so there's that's why in that case the mangrove isn't important. The waves are not important, sorry.
Yeah. If anyone else has any questions, please feel free to ask Ruth. She's very busy, so if this is the time to get your questions about coastal change and sea level rise in. We have a question from Kina Leong. Sorry if I pronounce your names incorrectly. We have heard recently about climate change being a significant reason why we're losing Antarctica. How much of this polar cap melting could be resultant from sea level changes?
Absolutely. So I'll start by saying I'm not an expert in ice sheet modeling, but what I will explain is as following. Not only does the melting of the ice sheet contribute to sea level rise, the melting, the ocean itself contributes to the melting. So there are some feedback loops here where when you melt the ice sheet and you create more ocean touches the ice sheet from below, for example, and that can accelerate that melting. So how that melting gets distributed around the world is a very complicated story, but there is definitely a feedback between that melt and then the remelt of the ice sheet.
Okay, thanks, Hina, for that question. Kathy Yule has a question about mangroves. Are certain mangrove species better at trapping sediment than others? Example, Rhizophora versus Avicennia.
So that's a really good question, and I think almost Sabrina can answer that question for you. But what we find is that a disturbance to the flow is a disturbance to the flow. The actual detail of how much is in the way of the flow is less important. So, for example, when you cut down the vegetation, it still deposits. Sabrina measured sedimentation across huge areas with all sorts of densities of vegetation, and it's really important to have some disturbance there to the flow. So like definitely not have nothing, but like once you have it, if it's Avicennia or Rhizophora, not super critical. They won't occupy exactly the same, what's called the niche. So they're not always going to be successful. You know, one would be better in some conditions than others.
So Kathy's question was more or less relating to whether some would be better for replanting than others, but you just answered that saying that not all of them will be in that same niche, and they are very specific mangroves. Thank you, Kathy. We have a question from someone who wants to remain anonymous. Are there key places in Australia where the coastlines are being managed well and we can avoid erosion?
Yes. The short answer is yes. We can avoid certain amount of erosion, and we are doing that quite successfully actually here in Melbourne. So if anyone out here is in Melbourne water, like a shout out to you guys. I think Melbourne is quite well managed. I mean, like we do have some flooding instances, but they're not yet severe. Our beaches are well nourished. I mean, like we have a pretty successful nourishment program. So I do think we can see that. Australia is very big, right? So we need to think about managing shorelines is very expensive, and with and we can stop it. I mean, like with concrete, with all sorts of ways to do this. It might not be what we want to see out our window. It might have flow-on effects that are really detrimental to the environment. But to stop water, we know how to do that. And we know how to do that because I showed a photo there. It was like we have seawalls that were built 7,000 years ago to stop seawater flooding ancient cities, right? We've been doing this for a long time. The Romans have built walls. We have almost the entire of the Netherlands is below sea level. We are very good at stopping the sea from getting to where we want to, but we do need huge investment for that.
Thank you, Anonymous. And again, another question from Ashley. I think this might be our last question for the session. She was actually one of your students. So she said, from your marine unit, I remember that there's something called isostatic rebound. Just out of curiosity, will isostatic rebound affect the sand budget as well?
Absolutely. So when we talk about isostatic rebound, we're talking about for some reason, okay, say it's ice. Usually it's ice because ice is very heavy. It pushes the continent down. And when that ice melts, there's less weight on the continent, which is floating, and it can come back up. Okay, and when that happens, it means that the land and the ocean are diverging again, right? So when we move, for example, in the UK, the north of the UK is rising up, but the south of the UK is coming down because there was an ice sheet only on half of it. So the rebound is relatively slow. Usually areas that are rebounding, like Scotland, you won't have sandy beaches because the rate of rise from the ocean is too fast for sandy beaches to form. So that's kind of the feedback I can think of. In Australia, we don't quite have that type of tectonics. We didn't have an ice sheet any time in the recent past, and other processes that can cause isostatic rebound aren't really operating here. So our continent is moving very slowly. We're pretty set in our place.
We have 2 more questions, and this will be our last. Elisa Bull says, sorry, I might have missed this, but is it known why the mangroves in the Northwest Australia are expanding?
Yeah, so Alyssa, hello. So one of the reasons is because sea levels are rising and the shoreline is eroding there, which means we are stretching out the intertidal zone. We're moving the intertidal zone. It's a really big tide over there. There's a very long intertidal zone. So we have all this new area for mangroves to colonize. So we have an expansion that is a landward expansion. And another reason that's happening is changes in precipitation and areas. So, for example, you might have heard of the big dieback. These are things we're going to see less and less of as we go forward, as precipitation changes in those regions.
Okay. Not sure what to do with the last question. Okay, I'll just ask it anyway, and we can handle it however you see fit. The question is, from Anonymous, have the models you have used provided evidence of climate change?
Yes, so I'm going to start by saying the climate changes all the time. Climate changes from day to night. We have changes in climate that are happening all the time. But we can see trends of things happening over longer time scales. And for example, we can see changes in sea level. We have a 600,000 year record. So we saw like a bit of a stability in the last 2,000 years, but a big uptick close to now. So we're seeing impacts of climate change all around us. In terms of the model, we're seeing, for example, the wind distribution is going to be a bit different in the future. Things we see that are to do with climate change directly are a lot to do. Actually, not from that model, but if you look at vegetation, right? Because vegetation responds relatively quickly. Landforms, we're talking about slightly different timescales. But what is really quick is vegetation. And I don't know if you are from Melbourne, but expansion of what is a tropical species, like a mangrove, coming further south. So we're seeing that type of change. We're seeing changes to the East Australian current coming down lower and warming up the waters around Tasmania and the Bass Strait. So we are seeing changes. And one of the first things you're going to see is changes in the distribution of the biology, actually, which is really interesting.
Thanks, Ruth. I think we all learned a lot from you today.
Thank you.
Except we only had an hour, but I'll hand over to Udi now and she'll do the closing. Thanks to everyone for listening and being interested in this part of science. And we thank you for watching.
Thank you to both Ruth and Sabrina. That was a fantastic presentation.